In 2025, China completed 157 kilometers of highway without a single construction worker using a shovel. The entire project was carried out by 10 self-driving machines that worked together in formation while human supervisors watched from control rooms. These machines were not ordinary vehicles. Each one made thousands of quick and accurate decisions every second, guided by advanced sensors and satellites that could measure distances with centimeter-level accuracy. The outcome was not only the first major highway project built almost entirely by artificial intelligence, but also a clear look into how future cities and infrastructure may be built. The highway chosen for this groundbreaking project was the Beijing-Hong Kong-Macau Expressway, also called the Golden Channel. This road is one of Asia's most important routes because it connects the factories of the Pearl River Delta with China's northern economic and political centers. Every day, millions of vehicles travel on it. Large trucks carrying raw materials, passenger buses filled with people, and countless private cars. For China, this expressway is more than just asphalt and concrete. It is a lifeline that keeps trade alive, connects families across great distances, and drives economic growth. But it has also faced serious problems in the past. In October 2015, during China's National Day holiday, more than 750 million people traveled across the country at the same time. At one toll station, 50 lanes of traffic were forced into just 20. The result was one of the largest and most famous traffic jams ever recorded. Cars stood motionless for hours, stretching endlessly toward the horizon. From the air, it looked like a frozen river of steel. The world's media quickly called it Carmageddon, and the images became a symbol of how even modern infrastructure could collapse under extreme demand. For China's leaders, this was more than just embarrassing. It showed a serious weakness. The country's roads and bridges were modern, but they were still at risk of being overwhelmed. Traditional construction methods depended on thousands of workers, long building schedules, and constant risks of accidents or delays. Even with large investments, the pace of human-led construction could not match the country's rapid growth. The 2015 traffic disaster became a turning point. China realized it needed new methods to build and maintain roads faster, safer, and with more precision than humans could achieve alone. This challenge led engineers to consider whether machines could replace traditional crews. China was already ahead in automation, using advanced robots in ports, factories, and logistics. Expanding artificial intelligence into road construction was bold, but it seemed possible. Over the next 10 years, researchers worked on developing self-driving pavers and rollers that could move in formation, learn from live data, and achieve a level of accuracy that surpassed even the most skilled human crews. By 2025, the technology was ready to be tested, and the Beijing-Hong Kong-Macau Expressway became the proving ground. When construction began, the scene was unlike any road project ever seen before. There were no human drivers in the vehicles, no workers in reflective vests directing traffic, and no foreman shouting orders. Instead, 10 enormous machines lined up like a mechanical army, each one controlled by its own intelligence system. Human supervisors stayed in control centers far away, monitoring streams of live data on screens but rarely needing to intervene. The leader of this robotic team was the SAP 200C10PA paver. This machine was so advanced it could spread asphalt across 4 lanes of road in a single pass. Its screed was more than 19 meters wide, enough to cover the full width of the expressway. Moving slowly and steadily, it poured a glowing ribbon of hot asphalt across the roadbed. To an observer, it almost looked like a giant mechanical whale moving smoothly forward, while underneath its steel body, countless sensors and processors worked in perfect harmony. Behind the paver came the rollers, moving in a carefully designed formation known as 1+3+3+3. The first group contained 6 steel rollers, each weighing 13 tons. Their task was to press the fresh asphalt while it was still soft, creating an even surface. The next group included 3 rubber-tired rollers, each weighing 30 tons. They finished the compaction process, pressing the asphalt until it reached perfect density. Together, the machines moved in rhythm like a choreographed performance, automatically adjusting their speed, distance, and pressure based on live data rather than human commands. What made this project so different from earlier automation attempts was the level of independence these machines had. They were not simply following pre-programmed routes. Each machine made thousands of small decisions in real time. If the road surface was uneven, the paver automatically changed its screed angle. If the asphalt was too soft or too dense, the rollers changed their pressure. Sensors constantly measured heat, density, and alignment, feeding information into algorithms that grew smarter as the work continued. Humans only stepped in if something malfunctioned. The precision was possible because of China's Beidou satellite system, which provided positioning accurate down to the centimeter. Combined with radar, LiDAR, and infrared sensors, the machines could sense their environment with incredible clarity. They always knew the exact edge of the pavement, how much pressure was needed to remove a weak spot, and how fast they needed to move to keep the surface uniform. For engineers who had spent decades training human crews to achieve consistency, watching the machines do it perfectly without hesitation was astonishing. Safety was another major achievement. Road construction sites are usually very dangerous, with heavy equipment, extreme heat, and loud machinery creating constant risk. By removing human workers from the active site, accidents were dramatically reduced. At the same time, the machines were equipped with advanced protection systems. Each one had electronic fences, invisible safety barriers that triggered an instant stop if an obstacle entered the danger zone. Cameras and radar constantly scanned for hazards, and all the machines were connected by a communication network so that if one paused, the others immediately adjusted to stay in formation. One of the most impressive breakthroughs was a process called zero-edge rolling. Human crews had always struggled to compact asphalt right at the road's edge without breaking curbstones or leaving weak spots. The autonomous rollers solved this problem using advanced tracking algorithms that allowed them to follow the exact line of the pavement with millimeter precision. The result was a flawless road surface that needed almost no corrections afterward. The engineers who examined the finished lanes were surprised at how clean and precise the edges of the road were. They said it was some of the best work they had ever seen. The technology inside each of these machines was the result of years of hard work by Sany, one of China's top heavy machinery manufacturers. The engineers faced challenges that had never been dealt with before, like teaching a roller to sense whether asphalt was compacted correctly. To solve this, they created what they called fusion self-sensing high-precision positioning. This system combined information from many sources at once, including infrared heat sensors, pressure monitors, GPS signals, and cameras. All of this data was blended into one complete picture of the environment, allowing the machines to make automatic adjustments in real time. These decisions happened faster than any human crew could manage, ensuring accuracy and consistency across the entire project. The difference in efficiency compared to traditional methods was striking. Normally, building a highway of this size would require dozens of workers across multiple shifts. People needed breaks, meals, and time for coordination, and mistakes often meant delays or costly repairs. The machines, however, worked without tiring. They stayed in perfect formation hour after hour, with no need for handovers or constant supervision. This meant projects that used to take months could now be completed much faster, with fewer flaws and less rework needed afterward. From the control rooms, the supervisors compared the process to watching an orchestra. The machines were like steel instruments, each playing its part in harmony. Screens displayed real-time data, including temperature curves, compaction levels, and exact positions of every vehicle. Supervisors had the power to step in if necessary, but most of the time their job was simply to watch as the machines carried out their tasks with flawless precision. Every kilometer built also produced more data, which was saved and analyzed to improve future projects. In a sense, the machines were not just building the highway, they were learning how to build even better ones in the future. Observers who visited the construction site noticed how quiet it was compared to normal road projects. Instead of the constant noise of shouting workers, clanging metal, and chaotic movement, the only sounds were the low hum of engines and the soft hiss of asphalt being laid down. Without people moving around the heavy equipment, the site felt almost sterile, more like a science lab than a dusty construction zone. Yet this calmness was exactly what made the project so powerful. It showed that roads could be built with less disruption, fewer accidents, and more consistent results. The success of this robotic crew was more than just a technical victory. It marked a turning point in the history of construction. For thousands of years, roads had been built with human labor, from the stone paths of ancient Rome to the massive highways of the 20th century. Now, China had proven that machines could take over nearly every part of the process. These 10 autonomous giants were not the end of the story but the beginning of a new one, where infrastructure might one day rise without any human hands at the site. But this new way of building also raised questions. What does it mean for safety, for costs, and for the people who used to do these jobs? Road construction has always been one of the most dangerous professions, with workers spending long hours under the sun, surrounded by heavy machinery, traffic, and noise. By removing people from the front line, accidents could be reduced, but new risks also appeared. Engineers designed multiple layers of safety into the autonomous system. Every vehicle had radar and cameras that constantly scanned for obstacles, along with invisible electronic fences. If something entered the safety zone, the machines stopped instantly, reacting in milliseconds. Unlike humans, who could be distracted or tired, the machines never lost focus. Another key breakthrough was the communication system that linked all 10 machines together. Each vehicle worked independently but also shared information in real time. If the lead paver slowed down because of an irregularity in the surface, the rollers behind automatically matched its pace. If a sensor detected a hazard, the whole group adjusted instantly, shifting formation as needed. In traditional projects, miscommunication often led to mistakes, delays, or wasted resources. Here, the machines functioned like a single organism, reacting faster than humans ever could. The financial benefits were also massive. Normally, a highway of this size would need hundreds of workers across long shifts, costing tens of millions of dollars just in wages, housing, food, and transportation. With autonomous construction, the workforce was reduced to a small group of supervisors and engineers. While the machines themselves were a major investment, their efficiency and reliability made the project more cost-effective in the long run. Roads could be built faster, cheaper, and with better quality. The machines had no need for overtime pay, medical leave, or days off. If the weather and conditions allowed, they worked non-stop through the night and still produced results that matched or even went beyond the usual quality standards. For Chinese policymakers, this project was about much more than simply building a highway. It was a test to show how a new model of infrastructure economics could work. China planned to add thousands of kilometers of new highways, bridges, and tunnels over the next few decades. By reducing labor needs while increasing precision, the country could save enormous amounts of money. Faster construction also meant that important transport routes would not be blocked for long periods, which was critical for a road like the Golden Channel. As the main artery of national commerce, every extra day saved from construction delays translated into billions of dollars in preserved productivity. But behind the impressive numbers, there was also a human concern. What would happen to workers when machines began to take over their jobs? Road construction had always employed large groups of people, many of them working on short-term or seasonal contracts. These jobs were often the main source of income for entire families. With the rise of autonomous construction systems, critics feared that thousands of workers could be left behind, struggling to find work. On the other hand, supporters argued that while some traditional roles would disappear, new kinds of jobs would be created. Machines needed people to design them, maintain them, and supervise their work. Instead of spending long hours under the sun with a shovel or roller, future workers might sit inside air-conditioned monitoring rooms, writing algorithms, analyzing data, or repairing advanced sensors. This debate between job loss and job transformation was not unique to construction. The same concerns had already appeared in industries like manufacturing, farming, and delivery services as automation spread. What made the Golden Channel project so important was that it showed this shift had now reached infrastructure, one of the last areas still powered mostly by human labor. For centuries, building roads was the image of hard physical work. Now it was becoming a field where knowledge of data, engineering, and machine learning mattered more than strength or endurance. Many observers also noticed the strange emotional effect of watching machines carry out work that people had done for generations. Some found it fascinating, even beautiful, to see machines moving in such calm precision, without hesitation or mistakes. Others found it unsettling, almost alien, as if the machines were replacing a deeply human tradition. For older construction veterans, it felt like watching their profession change into something unrecognizable. But for younger engineers, the sight was inspiring. They saw it as a sign that they were entering a new age, where infrastructure projects would be built with the same technological expertise as airplanes, satellites, or microchips. The supervisors in charge of the Golden Channel project said their jobs now felt more like air traffic controllers than traditional foremen. Instead of shouting orders on a noisy site, they sat in control rooms surrounded by glowing screens. These screens displayed streams of information, including temperature levels, pressure readings, maps of machine positions, and live video feeds. Their main role was to watch for unusual behavior and step in if something went wrong. But in reality, the machines handled almost all the adjustments on their own. Supervisors often spent more time studying patterns in the data than giving direct commands, trying to understand how the systems were learning and improving with every kilometer built. The machines on the Golden Channel project greatly reduced the need for large crews of laborers, but at the same time, they created a growing demand for skilled technicians. Universities and training centers in China had already begun adjusting their programs to prepare students for this new reality. Instead of training workers only for traditional construction jobs, they were offering courses in autonomous systems, robotics, and advanced maintenance. Just as the spread of factory automation gave rise to entire fields of robotics engineering and software development, the expansion of autonomous construction was beginning to shape a new generation of specialists. These professionals would not control single machines but manage and supervise entire fleets working together. Safety, economics, and labor were all tied together in this transformation. The Golden Channel project proved that highways could be built more quickly, at a lower cost, and with fewer risks to human life. Removing workers from dangerous frontline positions meant fewer accidents and injuries. Yet it also raised important questions about how societies should adapt when machines take over work that once supported millions of families. The project did not resolve this debate, but it provided the world with its first working model of what fully autonomous infrastructure looked like. Policymakers, economists, and workers everywhere were forced to think about a future where highways, bridges, and tunnels could rise from the ground with almost no human hands involved. For China, the lesson could not have been clearer. The traffic disaster known as the 2015 Carmageddon showed the heavy price of outdated construction methods. A decade later, the Golden Channel demonstrated the potential of a new model, turning a past embarrassment into a showcase of progress. By completing such a massive project with machines instead of people, China positioned itself as a global leader in autonomous construction. While other countries were still debating regulations and raising safety concerns, China was already laying down asphalt with machine precision, proving that what others only discussed could actually be achieved. If machines were already capable of building highways, the next question was obvious. What about bridges, tunnels, and even entire cities? The success of the Golden Channel was not the end, but the beginning of a larger plan. Engineers explained that highways were simply the first step. Work was already underway to apply automation to bridge construction, tunnel boring, and even the assembly of massive residential blocks. The long-term vision was to create infrastructure networks that could grow almost entirely without human labor, guided day and night by artificial intelligence, satellites, and sensors. Other nations quickly noticed China's achievement. Japan began preparing robotic crews for the 2030 World Expo. The European Union started studying China's methods to see if they could be applied across member states. Even the United States, despite ongoing trade tensions, quietly increased its funding for autonomous road construction research. But China's strength was not only in technology, it was in speed. Where other nations hesitated and debated, China built. Each new project added fresh data, sharper algorithms, and more confidence that the future of construction belonged to machines. The Golden Channel was 157 kilometers long, built by 10 massive autonomous machines. But its importance went far beyond numbers. It was more than a milestone. It was a declaration that the age of human-only infrastructure was ending. Roads, bridges, and tunnels would always serve people, but they might no longer be built directly by them. China had proven what was possible when technological ambition met national determination. The question was no longer whether this model would spread, but how fast and who would take the lead. For centuries, infrastructure was built through human effort, stone, steel, and sweat. From this moment forward, it might instead be built through code, sensors, and machines. The future of construction had already begun, and the Golden Channel was its first great example. Those who want to see what comes next, the unbelievable projects these machines are already preparing to tackle, must pay attention now, because the future of our cities and roads is being built before our eyes.